Welcome to another physics math review video. This video is going to tackle the graphical analysis part of your summer assignment. So let's move into the overview. All right, how to interpret a graph. So there's going to be two different ways of interpreting a graph here that we're going to go over, other than just obviously being able to look at the points on the graph. That I'm not going to go over in this video. So the first one we're going to go over is how to find a slope. Slope, that was actually a question or part of a question on the FRQs for this year's AP exam. Just knowing how to do a slope got you 1 point, and then the extra point was understanding the physics behind it, essentially, and using a proper idea in physics to get the slope that they were asking you to find. So if you forgot how to do slope, here is the equation for it. Slope in math terms is rise over run. A better way to write it out here is the change in y over the change in x. So a change in anything is final minus initial, or for this situation, it's going to be y2 minus y1 over x2 minus x1. So looking at this, we're going to pick 2 points on either your best fit line that you would create. So for a best fit line, if you're creating that, you just want to have, based on your data points, you want to have some data points above the best fit line, some data points below the best fit line. You're not trying to connect all the dots. In the example that we're going to do here, they just give you the lines, so you have to worry about creating that. So with this, you're going to pick those 2 points out. Probably the easiest ones you're going to use where they actually line up with numbers on the actual graph. Determine the difference in the y coordinates. So just do your y2 minus y1. That's your rise. Determine the difference in the x coordinates. Do your x2 minus x1. That is going to be your run. Then divide the difference for the two. So do the change in y over the change in x, and you're going to end up with the slope of the graph. The other way to interpret a graph that we are going to go over today is getting the area under the curve. This situation we're going to use is a velocity versus time graph. So to find the area under the curve, what this essentially does is it gives you some kind of physical quantity as well. Because when you do area under the curve here, you're going to end up with different units that will give you some type of physical quantity. We have both here a rectangle example and a triangle example. Obviously, for a rectangle, if you did happen to forget this, the area under the curve is going to be A equals just base times height. Whereas for a triangle, the area is going to equal 1/2 base times height. And what this does essentially, again, it's going to give you some units that are going to be akin to a physical quantity. In this situation, I have velocity times time. If I plug in what I have here, my base of so let's just go through and do this just to show it. So my base here is 6 seconds, and my height in the rectangle example is going to be 30 meters per second. What I do there, when I multiply the two numbers together, I get my new number here. So 6 times 30 is going to give me 180. Then I'm going to also multiply the units together here. So I have 180. If I'm looking at my units, I have seconds on top, seconds on the bottom. So my seconds cancel, and I'm just left with meters. And we learned yesterday that meters is going to be distance or displacement. So that's how I get, say, distance or displacement from a velocity versus time graph. You can also do this with an acceleration versus time graph, which I'm not going to show here today. But same idea. Once you get the area, you can get a unit from that, and that gives you a physical quantity that you can use. This goes throughout physics. You're going to see this over and over again. It's an idea both in AP and Regents, so you see this throughout the entire year. Another part of graphical analysis is graphical relationships. This is really important in Regents for some of the multiple choice questions. It's also important for AP when we have to linearize graphs. So we have here at the very top, you have that symbol there that kind of looks like the Greek letter alpha, but it is not. It just means proportional to. There's no like special name for it. That's all it is, just proportional to. So when we have here y is proportional to x, means y is proportional to x. So you just have that symbol where y is going to equal cx, and we're going to see this in the equations that we do for these examples, where c is a constant, so y is proportional to the constant multiplied by x. We have our relationships here. Linear relationship is probably a relationship you've seen the most in previous math classes, certain things like that. You probably have also seen the other relationships, but linear is the most common, I would say, up to this point. This just shows y is proportional to x, and it's going to look as y equals the constant times x. There's not going to be any squared or anything like that, and the shape of the graph below that is just going to be a straight diagonal line. The other one here, we have quadratic or a squared relationship. This shows that y is proportional to x squared. The equation is going to look as y equals cx squared. So you're going to have some value or some physical quantity is equal to this as a constant times whatever else is going to be changing. The shape of this graph is going to be a curve going upwards. We have our other two relationships that you'll see. They look fairly similar to each other. Sometimes in the Regents, they don't really make a change between these two, even though they are different. But it just depends on how they decide to write their questions. So you have an inverse relationship and inverse squared relationship. Your inverse relationship is going to be y is proportional to 1 over x. So you're going to have some constant or nothing, which is 1. 1 over x, so y is equal to constant times 1 over x. That graph is going to be a downwards curve. And then the inverse squared relationship looks fairly the same. Y is proportional to 1 over x squared. Y equals my constant times 1 over x squared. And this is also a downsloping curve, but it's a little bit sharper, or a little bit like steeper on both ends essentially. So let's move into our examples for this. All right, so our first example here is going to deal with getting the slope of a graph and then being able to figure out what type of physical quantity we have based on that. So if you don't know what the units are, you don't need to know them yet at all. I have them in the summer assignment, or you could look it up online as well. So your first thing here, given the graph above, calculate the slope of the graph using the best fit line, so it gives you the best fit line already. Include the formula used and substitution with units. So formula used and substitution with units, that's a very important idea in Regents physics. It's not an important idea at all in AP Physics 1. You never have to do that. You're not going to lose points if you don't show units. If it is ever a math question or a straight up just calculation question, that rarely ever comes up on the part 2s. So you don't really have to worry about that. But unfortunately, again, take the Regents at the end of the year, so you do have to worry about that idea for that exam. So what that just means is putting in the units that they give you in a situation. If I'm finding the slope, again, slope is going to be, so I'll just write out slope. That's going to be equal to my change in y over my change in x. So for this, that's going to be, again, y2 minus y1 over x2 minus x1. So it's going to pick out, based on the graph, what my y2 is going to be, put in the units with that, do the same thing with y1, and the same thing with x2 and x1. So when you're doing this on a graph, you want to pick points that line up with the axes nicely. So for this one, the first one that I see that jumps out to me on the line, I can go pretty much all the way to the top, or you can go all the way to the top if you like. I'm going to go one step below that and go to 20 and 4 here. So we have 20 here. That lines up with 4 seconds. So on the top for my y2, this is going to end up being 20 meters per second. Then we're going to have on the bottom my x2, and this is going to be 4 seconds. So maybe asking why I'm calling this y2 and x2, even though these are the first ones that I picked out. That's just because I'm looking at the graph and I'm reading it either left to right or down to up. That's going to be the stuff that comes second after my first point that I'm going to pick here in a moment. So I have here, so let me make the line a tiny little bit bigger. So my next dot that I'm going to pick on a line, I'm going to go all the way down here to 10 and 2 where this lines up. So again, 10 meters per second is going to also line up with 2 seconds. So that's going to be my y1 because that is the first thing that I see on the graph before the 20. So that's 10 meters per second over my time here, which is just 2 seconds. So now I just plug this into my calculator, or I do it straight away. I have 20 minus 10. That's going to give me 10 meters per second. Over 4 minus 2 is just 2 seconds. So simplifying this one step further here. So slope is going to be equal to 10 over 2. That is going to give me 5. And then my units, I'm just going to put this on the top here. I have meters over seconds, and then seconds over 1. If we do this, we multiply the outsides and then multiply the insides. So I should have then meters on top divided by seconds times seconds. So that's going to be seconds squared. So my slope here is going to be 5 meters per second squared. So now I can look into my claim. This is my evidence from the graph. Now I have my claim. Use the evidence above to make a claim by filling in the following blanks. The slope of the speed versus time graph is equal to, we just figured this out, is 5 meters per second squared. That's my number with my units. And then my units here, the meters per second squared. If you go into your packet where dimensional analysis is, there's all the units there for everything. I added there at the end a couple of ones that I said you had to use for later. And you should see there that meters per second squared is going to be the unit for acceleration. So we should have here 5 meters per second as my answer. And my physical quantity is going to be acceleration. All right, so let's move into our examples, our other examples for graphical analysis. All right, so examples 2 and 3 are going to deal with our graphical relationships idea. So that's going to be looking at an equation and figuring out, based on what they tell us the graph, what is the relationship between those two quantities, and then what is the shape of that graph. So we have here an equation you will use later in the year, is for force of friction, which is Ff equals mu Fn. What I have with this equation, there are little letters next to both the F's. This is what is called a subscript. It basically tells you what that force is going to be. You can use that in any portion of physics. You can use it for velocity. You can use it for acceleration, types of energy, things like that. Mu there is a Greek letter. It looks like a U, and you'll see it many times throughout the year. So for this, given this equation, what is the relationship between the force of friction Ff and the normal force Fn, when the coefficient of friction mu is a constant? So what I'm going to do here is write out my equation, use the y equals x, and see what type of relationship we are going to have here. So my equation again is Ff equals mu Fn. And based on this, looking at what I'm given here, my force of friction, FF, is going to be the Y. It tells me that the constant is going to be my coefficient of friction, mu. So then my X is going to be the normal force, because that's what I'm graphing the Y against. So if I look at this here, I have Y, and the Y should be directly proportional to X here. So if I wrote this out, FF is directly proportional to Fn. So this is going to give me a linear relationship. So then what is the shape of this linear relationship? So if I draw out the FF versus Fn graph, so this is my Y versus my X, which is the normal force Fn. I am then just going to draw the graph here. So my slope is going to be in red, and I should have a straight diagonal line to the best of my ability here. That's what the graph should look like, since we have a linear or a just direct relationship. So let's move into example number 3. Our last example for today's video, we have here an equation you will use later in the year, is for potential energy of a spring, U subscript x equals 1/2 kx squared. So given this equation, what is the relationship between the potential energy of a spring, U subscript s, and the spring displacement x when the spring constant k is a constant? So again, same idea as the previous example. We're just going to write out my equation here. So I have here U subscript x is equal to 1/2 k times x squared. So then we have here my US, that's going to be my Y. My 1/2 k, 1/2 is a constant, and it tells me that the k in the example is also a constant, so that's going to be my C. And then x squared is going to be my x squared. So I have here then that my US is going to be directly proportional to my x squared, and that is going to give me a squared or a quadratic relationship. So that is part A done. So then looking at part B, we see to see what the shape of the potential energy versus just spring displacement graph is going to be. So I'm going to put here on the y-axis my U subscript s, on the x-axis just x. I'm going to talk about this in a second further, but this is just for this shape of the graph. So we have here U subscript x over x. Again, I'm going to do my slope in red. So this should give me a curved upwards graph like so. All right, if you did also as well want to linearize this graph, which you do not have to do, there should be a little bit of a hint in part A of what you should graph in order to linearize this, but you do not have to do that. That's something we will go over during the year. That is a very important idea in AP Physics 1, but for the summer assignment, do not worry about it. This is all you have to do for these types of questions on the summer assignment. So I hope this video was helpful. I will get up the rest of the videos by the end of the week, and good luck with the rest of the summer assignment.